prepare yourself for some exciting remaining talks about code generation. The first talk will be by Christopher Brix, talking about generating verified assembly code using Dafny and reinforcement learning. That's very exciting since I don't think we've heard any AI today, so this will be the first AI. So yeah, thank you.
Great. Thank you very much for the introduction. I'm Christopher, and today I would like to talk about reinforcement learning with Dafny. What I'm going to present was joint work with my supervisor when I did my internship at Amazon in the as an applied scientist intern in the Amazon Web Services team, automated reasoning. Yeah, and Tristan was my manager back then. And today I would like to talk about the results of that internship. So maybe you noticed a few months ago, last year, there was a paper called Faster Sorting Algorithms discovered using deep reinforcement learning, published in the Nature magazine by Google DeepMind. And there they talked about an algorithm called AlphaDev. And AlphaDev was used to generate assembly code for several tasks. One of them was sorting sequences of integers. And crucially, this AlphaDev algorithm was able to come up with assembly programs that use fewer instructions and had less latency than the prior human benchmark. So they were able to improve this assembly implementation using reinforcement learning. And for my internship, I looked into how we can extend AlphaDev, possibly using Dafny. But before I'm going to talk about Dafny and how it can be used here, let's talk a bit about artificial intelligence and reinforcement learning, because that's kind of the important concept here. So in reinforcement learning, you treat your problem as a game, and then you teach an agent to play this game. So for example, we could say that the game is chess, and we want our agent to learn to play chess. So the agent, in some way, is defined as a function that receives as an input all the information it needs about the current situation of the game. For example, all the locations of the pieces on the chessboard. You could also use the picture of a chessboard with the pieces on it as an input. Then you would have the color values of the pixels in the image as an input. And the agent is then tasked to come up with a move, and we'll eventually use some heuristic, some external oracle to evaluate whether this move is good or not. So in this example here, our agent predicted to move the white knight to capture the opponent's queen, and that's a good move, we decided, so it gets a positive reward. And eventually, the agent collects experience in the game and is able to learn what moves yield a positive reward. So over time, it will come up with a strategy to maximize those rewards. And then we can say that it has learned to master this game. In deep reinforcement learning, the agent is implemented using a neural network. So we have our neural network that receives the current state of the game encoded. And as an output, we predict the next move that the agent wants to perform. But we also predict the reward that the agent expects to receive for this action. And here, the benefit is that we can then we can compare the actual reward that the agent receives with the predicted reward, and eventually the network will be trained such that the agent is able to predict the reward correctly. And at that point, we can use the agent to have a strategy to maximize the rewards that we get. Okay, so this was a very short general introduction to reinforcement learning. But what is AlphaDev in particular? So AlphaDev is a deep reinforcement learning algorithm. And here the game wasn't chess. Instead, it was to generate assembly programs to solve a given task. And in their paper, they focused on sorting sequences of integers, I think up to length 8. Here for this example, I picked the task of reversing a list of 4 integers. You can basically insert any task that you're interested in. Now, because we've changed the game, the input of our program changed. We can also see this in the formal definition of our agent. It's no longer the pieces of a chessboard. Now it's a partial program as well as exemplary memory and register values. So what does that mean? The idea of our game here is that we'll start with an empty program, and then a move in our game consists of adding a new instruction. So in the second move, you already have a partial program that has one instruction, and you'll append a second instruction. And you keep on appending new instructions until eventually you've solved the given task. So here the current program already consists of 2 instructions, and then we also have a snapshot of the current memory and register values, and that just means that we've randomly sampled a possible input that our program could receive, and we've executed the partial program on this input. And this isn't strictly necessary, but it helps the agent to reason about how the individual instructions modify the state of the machine, so it's able to learn faster and generate code programs easier. As before, in the chess example, the agent now has to predict a move. Here, the move is a new instruction that should be appended to the program. An external oracle decides that this was a neutral move. There's no reward. We append the instruction to our partial program, and we repeat this process. So now the input has been updated. The agent predicts a new output, a new instruction, and this time there's a reward because in this situation we have partially solved the task. Okay, so again, over time, the agent will learn what kind of moves and what kind of sequence of moves yield positive rewards, and will favor those, and over time generate very efficient programs, because moves that receive negative rewards or neutral rewards are avoided. Okay, in the paper about AlphaDev, the authors highlight one problem, and it's that the generated program generated by the agent isn't known to be correct. It could have a bug in it, and to make sure that the generated code is correct, they test it, and they do that exhaustively. So for sorting sequences of integers up to length 8, you can just enumerate all possible input permutations, and you can prune away most of them because lots of input permutations are actually equivalent. If you restrict your operations, you can perform on this list sufficiently. But still, as you increase the length of your sequence, the number of test cases that you have to run through increases exponentially. And you can see this here in this plot. Testing eventually becomes infeasible. So this was kind of the motivation why we wanted to integrate Dafny in this pipeline. Okay. So the proposed solution here is to use Dafny, because using Dafny we can have a problem specification written in Dafny. We can then use reinforcement learning and eventually receive assembly code that's not just tested to be correct, but actually verified to be correct. Okay, so how can this be done? And the way we did this was to provide Dafny with some code to allow it to reason about how each individual assembly instruction would change the state of a machine that executes this code. So first we start with an enumeration of all the assembly instructions that we want to support. So here this is a subset. For example, we want to support moving a value from memory to a register. We want to have comparisons between two registers, and we want to have conditional move operations dependent on the prior result of the comparison. This is just the enumeration of all the instructions we want to support. And then we have some logic that defines the state of a machine that would execute this code. So here we have a list of all the memory and register locations. We would also list the flags that are used for the comparisons and so on. Based on the state of a machine, we can then define how the state can be mutated. So, for example, we can write to register, and that means that the respective register location is updated, the state changes, and now we store the updated value in this location. And we'll have similar functions for writing to a memory cell, writing to a flag, and of course also reading from all of those locations. Finally, here in this block of code, we need to map from our instructions that we want to support to a sequence of read and write operations on our state. For example, if we want to move a value from memory to a register, we first have to read that memory location, and then the resulting value is written to a register, and the state is being updated. And we write this mapping for all of the instructions that we've defined in the beginning. This is a little bit of work, but you only need to do it once, and you only need to update it if you increase the set of assembly instructions that you want to support. Then we write down the property that we want to verify for the assembly program. So, for example, if you want to swap the order of a sequence of 4 integers, then we could write down that, yeah, the input and the output both have length of 4, and the output is in the reverse order compared to the input. Then we task our reinforcement learning agent with generating code for this. And whenever we have a new updated partial program that we now need to test to evaluate whether the task is solved or whether we need to continue with this game, then we translate this generated assembly code to something Dafny can parse. And this can be done automatically. So there's a clear one-to-one mapping between the assembly instructions generated by the agent and the instructions we defined at the beginning. So moving a value from memory to register and so on. And we just list, here on the right, we list all those instructions in sequence and then task Dafny to verify that when these instructions in this sequence are executed, then yeah, our property does in fact hold. Okay. Yeah, in the scope of my internship, I didn't get to look into the more complicated problems that the AlphaDev paper explored. I mainly focused on a simpler problem of swapping list of integers to keep the reinforcement learning aspect of this problem simple. But just for this problem, if we limit ourselves to a very small subset of assembly instructions of 32 possible instructions, then we have about 2 million possible programs that could be generated by permutating those instructions in different orders. This 2 million already includes that we've pruned away many different programs that just don't make any sense syntactically. If we now perform reinforcement learning on this problem, we can see that initially, so if you look at the yellow line here, initially at the beginning, none of the generated programs are correct. But then after, let's say, about 20 minutes and about 250,000 generated programs, the agent generates a correct program for the first time and then rapidly starts to generate those all the time. And crucially here, of course, we have not needed to enumerate all the different programs and verify all of them, but the agent was able to learn to generate a correct program faster than just enumerating all different possibilities. Of course, if you do reinforcement learning, performance is very important. So there are some tricks that you can apply. It's very important to generate games as fast as possible, so you've got lots of data to learn from. So we didn't perform the verification of the generated partial programs on the same machine. We moved that to the cloud. If your verification process takes any significant amount of time, then we can keep generating new games while in the background in the cloud the already generated programs are verified. And of course, we are doing machine learning, so we're using GPUs to parallelize our data generation. So we are not playing a single game at any given point. We are really generating like 512 different games at any given point in time. So if you take all of that together, then we've got thousands of games being played at any given time. And then there's a second possible improvement here. So there's no need to rely on Dafny for verification all of the time. So if we have a partial program and the verification fails, then Dafny can provide us with a counterexample. And if you keep track of this counterexample, then there's a high likelihood that if we append one instruction to this current partial program, then probably the program will still fail on this prior counterexample. Of course, eventually we hope that it will successfully run, but the likelihood that it still fails is high. So if you can keep track of this prior counterexample, we can first test it, just like the original AlphaDev algorithm did, before going to Dafny and verify only if the test cases have passed. Yeah, that of course reduces the runtime and allows us to generate games even faster. Okay, so in a comparison, if we are just using AlphaDev, then we would show the correctness of the generated assembly programs using tests. And if we are using Dafny, then we can now prove the correctness. And if we want to improve the performance further, then we can combine testing and verification and test in those situations where we have a hunch which possible inputs might constitute counterexamples. Dafny uses an enumeration of all possible inputs. That's not feasible for problems where the input space is large. And this is where Dafny can shine and verify the problem for all possible inputs. Because we can combine testing and verification for small tasks, basically we fall back to the original implementation and can solve this fast. And for large tasks, as I said, AlphaDev might not be applicable, but in the combination, this could now be solved. Okay, with that I conclude and take any questions.
Hi, so you use 32-bit data, and you said if you had to take the computer space, it would be like 2 million. So if we did 64-bit, it would be much more greater. But as you're considering machine learning, would it still take same amount of time in your method if we instead took 64 bits?
So the okay. So it's just to clear up possible confusion. It's not necessarily bits. It's possible instructions. So
Okay.
the number of assembly instructions that we wanted to support just happened to be 32.
Oh,
It's-
sorry. My question was like if you consider the data to be instead of 8-bit, or if you made it 16-bit, would there be a difference in time in your case?
So Daphne might have a harder time verifying this if we are
Okay.
actually verifying it on the bit level. So yeah, then basically if we go to this slide here, then the block where we do the verification, that might take longer, and that of course stretches the amount of time that any given game takes. So we'll then have more games running in parallel. The throughput would be the same, but the learning process would be a bit slower. Yeah.
Okay. Thanks.
You mentioned that in the machine learning, it gives a reward based on the program. And sometimes, even if it doesn't do the complete correct thing yet, you can already give a positive reward if it does a partially correct thing. So I guess you have some sort of clever evaluation function. I'm wondering, in the Dafny approach, where you have a specification to check whether the program is correct, would there be a way to also give this give a reward for a partially correct program by somehow being clever with the specification?
I would be, so I think there are ways to do this in a clever way. I did it in the stupid way of handwriting simpler properties. So if we are interested in reversing the order, then I also specified properties that the first index now has the value that previously was at the last index, and that the second index now has the value of the second to last prior index. You need to, with my implementation, you need to do this by hand, but it would be very interesting to come up with a solution to do this in a clever way.
I can think of something that's probably very stupid, but just an idea, which would be to sort of see how much difficulty the solver has with proving that the program is incorrect. Whether it immediately finds the counterexample or whether it would be a complicated one, something like that.
Yeah, that might be possible, yeah.
Okay, let's thank Christopher then, and